Welcome to the second part of video about chapter 2 basic concepts in traffic operations. Last time we looked at several terminologies that are used for traffic flow theory. For example, we looked at flow rate, density, speed, different kind of speeds that we use in practice, time mean speed, which is not used that much, but sometimes it's used, space mean speed, design speed for roadway design, speed limit, free flow speed, which we kind of derive from the speed limit. Then the relationship between speed, flow, and density. So this is fundamental relationship between speed, flow, and density. Then capacity of a roadway network, travel time functions, and some of the properties of travel time functions, delay, and what kind of delay is important for us to define level of service. And then we look into space-time graph. Space-time graph is usually used in synchro analysis. Now in this video we will look at statistical models. So in traffic operations, majority of the equations we used are statistical models. Like I mentioned last time, there are two kind of equations used in traffic operation. One is statistical model, which is about 90 to 95% of all the equations used in practice are statistical model. And then there is mathematical model. So mathematical model are rarely used, and one of the mathematical model we looked at last time was Q is equal to KV. Flow is equal to speed into density. So mathematical models always holds true, whereas statistical models, they are derived based on the data, and they are trying to fit the data curve or explain the data in a better way. So this is an important statement here. The majority of statistical model needed in practice are obtained from book, manuals, guidelines, and research paper. Although there are a lot of statistical model involved in the traffic operations, we do not actively go and build those models. So a knowledge of building the statistical model is for most part not as extensive as academia. When we are writing research papers based on several data, then we heavily rely on statistical model. For most part, most of the research is already provided in the books, manuals, guidelines, and research papers. So the majority of statistical model needed in practice are already given to us. We don't actively go and start building models every time we get data. There are only few instances where we use the statistical model by ourselves to analyze the data and make some meaningful conclusions. So we will discuss some of those instances where we have to use some statistical modeling techniques, derive some conclusions, or make sense of results based on these techniques. So the first and foremost, linear regression. Linear regression is one of the widely used statistical model in our field. So linear regression, as we know from our undergraduate study, is given by and so linear regression is a function where dependent variables are in a linear relationship with independent variables. By linear, we means the power of this dependent variable is 1. So the way linear regression is expressed is y, which is independent variable, is equal to first constant plus another constant times variable 1. Let's call x as a dependent variable, then another constant times variable 2, and so on. So this is how a simple linear regression is defined. The coefficient of linear regression can be estimated using several methods, such as least square method, which is a subset of maximum likelihood estimation method, quantile regression, least absolute deviation, etc. However, in practice, we mostly use the least square method. So there are building linear regression models and fitting the linear regression curve. But most widely used in practice is the least square method. I have not used or seen any other method being used. So another important factor is R square. R square is the statistical measure of fit that indicates how much variation of dependent variable is explained by independent variable in a regression model. R square value lies between 0 to 1. So a value of 0 as R square means they are independent of each other, which means this is my X and this is my Y. Then the values are spread all over the place randomly. And the value of 1 means they are perfectly in a relationship with each other, so they all the points will lie on a single line. R square value increases when more independent variables are used. So another important thing about R square is we can improve our R square, which is a measure of how good our model is. So R square is a measure of how good our model is. If it's closer to 1, then our model is better. However, we can simply improve the R square value by adding more dependent variables. So if we keep adding more variables, usually the R square goes up, performance of our model. However, keep adding the dependent variables to the model is not a good idea. It's kind of hardwires the model. So a good model is always written with least number of dependent variables, which is mentioned here. So R square value increases with more independent variables, even if independent variable is not significant. Adding too many independent variables is not desirable, as it can lead to overfitting of the curve. Adjusted R square is used to compare different model instead of R square. So there is another term called adjusted R square, which we use several times instead of R square. So when the number of dependent variable becomes higher, let's say greater than 7, then we switch from R square to adjusted R square. Adjusted R square takes into account of number of dependent variables in the equation. Next, we will look at z-test and t-test. So in FSWA simulation guideline is the first time there is a mention of t-test. And several DOT's guidelines are also available for the micro simulation modeling, and in some of the guidelines they use z-test, and in some of the DOT's guideline they use t-test. So at the beginning of my career, it has always been confusing on which guidelines to follow. So this is a very confusing topic, and a clarity is needed because some guidelines differ from another guidelines, and we have to just follow one of the guidelines. So we need to figure out ourselves on which one is the right way. So let's look at z-test and t-test. So z-test, one sample z-test is used to determine whether the sample mean is statistically different from population mean. We use the z and t-test in microsimulation modeling to figure out the minimum number of runs needed to achieve certain confidence interval, certain level of confidence to do microsimulation modeling, which is usually around 95%. So z-test can be used only if at least two of the criteria are satisfied. The first criteria is population variance is no, or second criteria is sample size is large, typically more than 30. So we use z-test if either population variance is known or sample size is large. This is our criteria to use z-test. If both the conditions are not satisfied, then we will use the t-test. So if population variance is unknown and the sample size is small, then the t-test should be used instead of z-test. So that's where especially for young engineers, it's very confusing whether we should be using z-test, t-test in the simulation modeling. So here That's the difference. So if we know the population variance, which we typically don't, then we will be using a t-test, and the sample size is less than 30, then we will be using t-test. If the sample size is greater than 30, then we will be using z-test. 30 is a kind of accepted number in traffic operations to consider a sample size being large. Usually the number of runs or data points for the simulation is around 10 to 15. So the z-score is given by sample mean minus population mean, if the population mean is known, divided by standard deviation of the population root over number of sample size, number of observation in the sample. For a given level of confidence, the critical z-score value is determined using z-table. We can do this in Excel as well. If the z-score is greater than critical value, then the sample mean is not equal to population mean. So we are looking for a z-score which is a lower in value. So we are aiming for a z-score lower in the value, so that sample mean is kind of equal to population mean. Some analysts do not prefer the idea of accepting or rejecting a hypothesis based on predefined confidence interval. In that case, the p-value is typically reported as a part of z-test along with z-score. P-value is a measure of probability that sample mean is statistically different from the known population mean. The smaller the p-value, the more important the variable is. Similar to one sample z-test, I have seen this in simulation modeling several times. There is two sample z-test. So these are not just mathematical concepts, they are used in our simulation modeling guidelines. Similar to one sample z-test, a two sample z-test is used to compare mean of two samples when population variance of both populations are known or their sample size is too large. Now let's look at the t-test. T-tests are also used in simulation modeling when the population variance is not known and the sample size is small. Then we will be using t-test. Similar to z-test, is almost exactly similar. T-score is given by sample mean minus population mean divided by this S is the standard deviation of the sample. So here we have this sigma, which is the standard deviation of population. Here we have S, which is standard deviation of the sample, divided by root over n. So the difference between z-score and t-score is this S versus sigma. Here sigma is known, then we will use z-test. Here sigma is not known, so we will use the S, standard deviation of the sample. If z-test is available, z-test is always preferred over t-test. So z-test gives better results or better confidence over t-test. So the first what we do is we look at whether we can apply and use z-test, and if z-test is applicable, then we use z-test. Otherwise, then we switch to t-test. The calculated t-score is then compared to the critical t-score from t-distribution table with n-1 degree of freedom and chosen confidence interval. If the t-score is greater than critical t-score is what we are getting from this t-distribution table, then the sample mean is not equal to population mean. So we will look at one example on how to calculate and how to interpret z-test and t-test. Let's look at the last concept under this modeling, which is GEH statistics. GEH statistics is traffic engineering formula which is used to compare traffic count with model traffic count. GEH statistics is given by this equation where M is the traffic volume from the model and C is the real world traffic count, and this is how GEH statistics is calculated. So in simulation modeling results, we want the GEH statistics to lie between 0 to 5 for 85% or more of our data. Now let's look at some examples. So we have here example 1, which is we are given some x and y data, and let's fit a linear, quadratic, exponential and logarithmic curve to this data using least square method. So in Excel I have put the data here. Typically what we can do is we can go to insert, go to this XY scatter plot and put the plots here. So this is my X versus Y. Now if I want to fit a linear curve, then I can just right click on data points and add trend line. This will fit a linear curve here. Now I will put display equations on the chart, and here I got the display equations. And if I can increase the font size to, let's say, 12. Now we'll notice this equation is matching the one we have on the left hand side. So this is how the linear regression works. So we can either insert this equation, or what we can actually do here is if we want to figure out the slope and intercept, there is an inbuilt Excel function called slope. So if I type slope, the known y's are these, known x are these, and then hit enter. So this is my slope using the slope function, which is matching the graph. And if I want to find intercept, then I will put intercept, instead of plus it will be equal to, then known y's, comma, known x, and this is my intercept, which is matching this number and this number. This is how we typically just do linear regression quickly in our Excel. So this is my slope and this is my intercept. So let's say I need to forecast this value for 15. So let's say I want to forecast it for 15, then I will write my final value is equal to slope multiplied by x plus intercept, which is this one. Hit enter. So this is my forecasted value for 15, assuming this is a linear curve. This is all we need to know. This is pretty basic and all kind of is needed for the linear regression. There are some important properties of linear regression which we will probably discuss when it comes to it. Now if we want to fit the quadratic curve for the same data, we can click on this trend line and then simply change to power and choose power as 2, or polynomial and choose polynomial as 2. This is the quadratic curve and the quadratic curve is here. If we want to put the exponential curve, then we can choose the exponential function here, and this is my exponential curve. Same with the logarithmic curve. This is the logarithmic curve. Now let's say we want to figure out this exponential in Excel. So instead of looking at this number, we want to produce this number. So let me switch this to exponential. Now what we want to do is, this is the linear curve, slope and intercept. If I want to produce this exponential curve, then what we need to do is take the log of both sides. So if we take a log of two sides of the exponential, so if you remember, our exponential equations are written as y is equal to a constant, let's say c, e to the power ax. If we take log on both sides, log y is equal to log c ln c plus ax. Now if we change this y to log y, log y is equal to ln. So this is my log y. Now if I assume log y as a new variable and x as my dependent variable, then I can notice that I have reduced this exponential curve to a linear regression. Now I can write my linear regression equations and still be able to use the linear regression to produce this exponential curve. So for this one, the slope will be, slope here is a. So the value of a here will be A, which is also slope of the linear curve, is equal to slope. Select the y's, select the x, that's it. Now intercept here, which is log c, is equal to intercept log y comma x. This is my intercept. So let's say I want to predict the value of 15 using this one, using this exponential curve. So the functional form is y is equal to c e to the power ax. So log c is this, so the value of c will be e exponential of this number. So now we know the value of c, we can calculate what is y. Y is equal to c multiplied by exponential of a multiplied by 15. This is my predicted value of based on the exponential curve of the, if the x value is 15, then based on the exponential fit my y value is 13.52. So there are different functional form. Ultimately we can reduce most of them to a simple exponential, simple linear regression, and we can use, or we can use this trend line. So either we can draw the trend line in Excel and use the equations, or if we actually want to dynamically have this number, we can write the equations like this by reducing the complex functional form into simple linear regression by either taking log or exponential. Now let's move to example number 2. In practice we use the linear curve very frequently and exponential curve very frequently. Logarithmic curves sometimes. Let's look at example 2. So the table, I have put the numbers here. The table below shows the travel time for 15 vehicles along a mile of roadway during an hour. So this is the travel time. If the population mean for travel time, this should be 10 vehicles, not 15. So I'll make that correction. So if the population mean for travel time was determined using historical 1 year travel time data, so if the population mean is 100 minutes, so this is a collected data in field for 10 vehicles. Now what we have is we have historical data for entire year for all the vehicles, and the population mean in 100 minutes. Population standard deviation is unknown, so use the t-test. Since the population standard deviation is unknown and the number of sample size is less than 30, we will be using t-test. So t-test is used when sample size is smaller, usually less than 30, and population standard deviation is unknown. Then use the t-test to check if the average travel time from the field collection is above the population average time at 95% confidence. So what we will do is, first we will go back to the equation. First we will figure out what is the population mean, what is the sample mean. So sample mean can be calculated using the function average in Excel. This is my x bar. Now mu is given to us as 100 from the example, and then I need to calculate standard deviation. So standard deviation is given by standard deviation dot p is for population, s is for sample. So now since we are calculating for standard deviation for sample, we will use the function stdev.s, and number of observation is 10, so n is 10. So here our t score will be, let's call it t score, is equal to, so first we have sample minus population mean. So sample mean, which is 108, minus population mean 100, divided by We have the standard deviation divided by root over 10. So the function for root is sqrt and this number 10. One bracket close, and that's all we need. So 5.65, this is our t-score, and we can go and look the t-score and 95th percentile, 95th% confidence and one tail, and the critical value is 1.883. So t critical is 1.833. Since the t-score is higher than t critical, so if we move back to our conclusions, so if the t-score is greater than critical t-score, then the sample mean is not equal to population mean, and in this case, since this is a positive number, its sample mean is higher than population mean at 95th% confidence interval. So this is how we use the t-test. So the way we want to see is whether this data, or let's say this data is from simulation, so we want to see whether this is actually replicating what is there out in field. So since this is our simulated data, we calculate the t-score, and the t-score is higher than critical t-score. So this simulated data is not equivalent to 100, which is observed data. So we will have to run more simulation or change some parameters. Now if the population standard deviation is 20 minutes, let's say it's given that the standard deviation is 20 minutes. Now use the z-test, because we know the standard deviation, we can use z-test, which is better than using the t-test. So anytime if we can use z-test, we will use the z-test. Otherwise, only if we cannot use the z-test, we'll use the t-test. So in this case, standard deviation is 20 minutes, which is pretty high. So let's check using the z-test whether this simulation data is good enough to match the population mean. So in the same way, we can calculate the z-score as, so for z-test, our mean will be equal to same as previous 108, population mean is still the same, and our standard deviation is given as 20, and number of observations are still 10. So instead of our t-score, our z-score will be 1.26, and the critical value of t, this should be z-score. The critical value of z-score at 95th percentile one tail is 1.625. 1.625. Since this is my z-score and this is my critical z value. Since my z-score is lower than critical z value, then my model simulation is kind of replicating this 100 minutes. That's what it means. It means this simulation is close. This simulation, given the standard deviation of 20 minutes, is close enough to the population mean, and we can consider the model calibrated. So that's how z and t tests are used. Well, that's all I have for this video. Thank you for your time. Thank you for joining us. And if you like it, please subscribe to our channel and share it with your friends.